Today, honor, and you will see it's also a great pleasure to listen to one of the Nobel Prize laureates that honored us with their presence at this ceremony of the opening of the International Year of Light. Professor Ahmed Zouil is one of those giants without whom there would be no progress in modern science, which was awarded by Nobel Prize. As we all know, Nobel Prizes are really given by for exceptional achievements. But Professor Zouil is also exceptional in many other aspects. He is a charismatic speaker. You will experience this in a moment. He is very much engaged with his roots in Egypt. He is of Egyptian origin, living in the States, very actively working to help a global development of peaceful thoughts and using science for peace. He became the first United States envoy of President Obama to the Middle East. He also was recently nominated one of the members of the Scientific Advisory Board of the Secretary General of the UN, Mr. Ban Ki-moon. It's really a great honor and pleasure to host him with us. Professor Zouil, the floor is yours. You are going to speak to us about light and life.
Well, it's a real pleasure to be here today and to begin this series of lectures. You heard quite a bit about the Nobel Prize, and there are 5 of us here. And I thought I'd begin by telling you what happened when you get the Nobel Prize. In 1999, it was announced for me, and there is a magazine, very distinguished, called Physics World, wrote about our work, because I bridge areas between chemistry and physics. And they got it right. What we did was my group, and why the Nobel Committee decided to give us the award. But then they went on after that to say, Zouil was born in Egypt in 1496. And so I was so glad to see that Sunas Vanberg here waited 500 years in order to give me the Nobel Prize here. What I'm going to talk to you about is an overview of light and life, celebrating this great year at UNESCO. So it is clear to all of us here that light is an essential ingredient from the universe's beginning to our world of today. This is an interesting slide showing the evolution of our universe from the Big Bang, which I hope I can get the here. See, from the Big Bang here, all the way until the evolution of ourselves and the creation of planets and we on the planets. One thing is very clear. Every time you see a yellow wave, this is what we'll call photons or light. So from 14 billion years on, we can see that light is part of our, not only of our life, but of the entire universe evolution. For this reason, these two people were awarded the Nobel Prize because you could see evidence or remnant of this light as early as possible from the Big Bang. And I'm sure you will hear from my colleagues about this in more details. So whether you're talking about time scale or you're talking about a length scale in the universe, and you will see some more examples of this from the Big Bang to the molecule that allow you now to see me as I speak. In all of this, light is central to the process. So imagine, with few examples that you probably know about, but I will re-emphasize, imagine life without light. First is the sunlight. Sunlight, in simple words, provide you with food, atmosphere, and the energy. Many other things, but to simplify it, we have the food, the atmosphere, and the energy. This is a process that you heard about, called photosynthesis. But I want to emphasize here there is a chemical process that is so essential that if you take carbon dioxide here and you have water, forget about the 6 and all of that. This is a molecule carbon dioxide. There is water, and you shine some light, you create sugar plus oxygen. So the carbon dioxide that would exhale, if it's mixed with water in the presence of light, it gives us the food that we need plus the oxygen that we can inhale. A process, it may appear simple, but it has taken billions and billions of dollars for research, and we cannot fully reproduce it. And there is a cycle here for this, going from the carbon dioxide to the sugar, called the Kelvin cycle, and for it, Melvin Kelvin was awarded the Nobel Prize. Imagine also that we don't have Mr. Edison's discovery of the light bulb. Just imagine that. So we're going from the candles and gas lamps into the light bulbs. And this is what we see for our own civilization. If there was no sun, and that's a remarkable thing for how we see, and I'll get to this a little bit, for vision, if there is no sun, we'll be blind because of the fact that light, as it gets into the eye, interacts with this protein. And there is a molecule in this protein called the rhodopsin, which, as it twists, as it just changes the shape, as you can see, then with a process that's initiated with the light, you can see me today with very high efficiency, even if I dimmed the whole auditorium. We wouldn't have synthesis of vitamin D if it wasn't for the light. Light goes through your skin, the yellow arrow, and then you make vitamin D, which actually regulates the calcium in our body. It's an incredible process in its complexity that if you know more about it, you realize we cannot live for even minutes without this process. So what is light? It's a big question. What is light? So first, I'll highlight a few things over a millennia. Many of the ancient civilizations, the Chinese, the Buddhists, the Hindus, also in all faiths, the Jewish faith, the Islamic faith, the Christian faith, light comes in. But I just highlight the theology, probably the first that's known to mankind, which is Mr. Akhenaten. Here shown, Akhenaten was Nefertiti, and they worshipping the sun, and this is the first time that actually we had a monotheistic religion in the world of today. Now, I'm getting into the Islamic Golden Age simply because to highlight few things in view of the very unfortunate and tragic event in Paris. It is remarkable that during the Islamic Golden Age, from the 8th century to the 13th century, these are just a few of the giants of the time: philosophers, chemists, doctors, physicists. You notice here, for example, maybe some names that you will not recognize. But for example, algorithm, which is known as al-Khwarizmi, in the whole area of the Arab and Persian area. Algorithm is where actually this name, al-Khwarizmi, is behind the name algorithms of today. Averroes, Ibn Rushd, one of the great thinkers in South Spain at the time. So this was truly the golden age of philosophy, of physics, of science, and the like. Today, I'll just say a few things about Al-Hazan, or Hassan ibn al-Haytham. You heard about him briefly, but I want to show you a few experiments that he did, and actually some scholarly work that has been published about him. I also pointed out here at the end Moses Maimonides. This was in South Spain. He is from Jewish origin, and I just want to point out that there wasn't the conflict of religion and conflict of civilizations and all of that that we are seeing, unfortunately, today. So here is Al-Hassan ibn al-Haytham, or Al-Hazan, and I'm pointing out just a few important things that he did. First, the Book of Optics, or Kitab al-Manazir. Second, the visual perception. Third, the camera obscura. All of the cameras we have today, the initial concept that, at least in the scholarly work that's known, is by Al-Hazan. And then he was a very interesting man when it came to philosophy and his opinion about reason and how to reason. And by the way, he claimed madness at one point in Cairo because he promised the ruler at the time that he can solve the problem of the dam near Aswan. And when he failed, the story goes that the ruler put him in jail, and then he had to claim madness, and he was released after the ruler died. But that's a story. I don't know if it's true. But this is very important here because this shows that in 1600, the two that were considered giants in reasoning and experimentation was Al-Hazan on the left here, and Galileo with his telescope on the right. We all in the modern world respect Galileo, and we know of his experiments. But I thought this was very important. It's actually pointed out by Sabra. Sabra is you can look it up, is a very distinguished historian and professor at Harvard who died recently. And so the books that's known very well is the Optics of Ibn al-Haytham, Inside the Camera Obscura, and of course the issue of the vision that I wish to tell you about. So prior to Al-Haytham, or Ibn al-Haytham, the theory was that we emit light from our eyes, and that's how we see each other. Ibn al-Haytham was the first to point out that actually the light comes in, reflected from the object, like a tree, and then get into our eyes, and that's how we can see. And this, I think, is a paradigm shift in the definition of the modern language of science. His idea of camera obscura was brilliant. The one on the right, if you can see it here, it's a candles, it's a group of candles, and there is a pinhole here, and the light goes through the pinhole and get into a screen. And of course, he showed that the image get inverted on the screen. The other representation here, you will see, I think, in the afternoon in more detail. So this is really the origin of the idea of the camera, because the image get inverted, and there's implication here that the light, of course, is going in a straight lines, and that's why you get an inverted image. And this, according to Sabra, had a major impact on the thinking of Descartes. So the transition then went to Europe, because it doesn't stay all the time, as was pointed out in the morning. Things change, and the transition went to Europe actually in the Age of Enlightenment and also the scientific revolution. And in my office, there is an interesting picture that was given to me, which say Einstein here, and he say, for the rest of my life, I want to reflect on what light is. Even Einstein is asking the question, what light is? And obviously we start with Isaac Newton, who thought that the light is a very tiny particles, and the famous experiment that he did to resolve the colors using a prism. So that was Newton's view of what light is. Then after that, in the about 1670s to the early 1800s, we had the wave hypothesis. So it's not only small particles, but we also have the wave hypothesis. People like Huygens and Fresnel. And this is a brilliant experiment. I think it's one of the most beautiful experiments in physics in all of history, one of. And this experiment was done by Thomas Young, who, by the way, was also an Egyptologist. And Thomas Young showed the interference of light. And this is a series of his lectures, and I'm sure you will hear more about this. So he showed if there is light going behind one pinhole, we get the normal pattern of light as you see it. But if we have two pinholes instead of one, then you get this interference between the waves that are coming out from these two pinholes. A beautiful experiment that had a huge impact on physics and the related area. And in the, I think one of the, again, most remarkable development was by James Clerk Maxwell, who told us that light is an electromagnetic wave. That means it has an electric field and it has a magnetic field propagating. And of course, he predicted what will be the propagation speed, which nowadays we call it the speed of light. And as such, Maxwell, I think he's a giant, Maxwell defined for us the entire electromagnetic radiation from the radio wave all the way to the gamma radiation, different frequencies and different energies. until Mr. Planck, Max Planck, defined what's called the quantization, and Einstein, of course, told us that the light that we see is bundles of energies that are coming at certain frequency, and the energy and frequency are related by what nowadays we call Planck's constant. Here in France, so some people said light is wave, some said that light is particles. Then Mr. de Broglie here, in his PhD thesis, pointed out that actually the two are related, and light as a particle can be associated with a wave, or even an electron with a certain mass can have a certain wave, and this was fundamental for which he received the Nobel Prize. So from this all and the nature of light, then came in the 50s and 60s what we call coherent light. This is a new type of light which generated to us new properties that we have not seen before. Properties that you can make light in pulses. Picosecond, which is a millionth of a second. Femtosecond is a millionth of a billionth of a second. Attosecond, a billionth of a second. You can generate ultra-intense light. You will hear from Gerard de Moreau. This is light really at the limit. Huge amount of intensity that you could put in these pulses. And you can create ultra-pure frequency, light that have very well-defined frequency for utilization in many things. This coherent light was credited for these three gentlemen, which you heard about already, and the Nobel Prize was awarded for them. The first laser was the ruby laser, which was made by Maimonides, and as you can see here, this is the ruby rod. And in fact, we celebrated the 50 laser at 50 here at the Louvre, and Professor Gerard Moreau was the chairman, and we had a great time here in the City of Light a couple of years ago. I just want to point out that here is Nico Bloembergen, here is Cohen Tanuji, and here is Charles Towns, and many others were at this celebration. My colleagues here will be talking to you about different things with this coherent light. You will hear quite a bit from Bill Phillips. Claude Cohen-Tanuji is not here, and Steve is going to talk about energy, not about cooling and trapping of atoms. But you can use these lasers to cool them down into micro and nano Kelvin, and you can also trap them. You will hear also about communication, optoelectronics, and the integrated circuits, and this is important work. And you will hear from Serge Harouche about nowadays our ability to manipulate an individual quantum state of light or of matter. Our own work that I want to share with you a little bit, some excitement that we are doing. You know, sometimes people think that after the Nobel Prize you go to sleep, but I just want to tell you a few things that we are doing. This was the old field that for which we received the Nobel Prize, called femtochemistry and femtobiology, and it had many, many applications. But we wanted really to not only to look at events that's happening in time, and that's what was the work that we did before. We wanted to look at space and time. We wanted to see objects and shapes, but this has to be in the microscopic world of atoms and molecules. So if you look at a very famous experiment that was done here in this country, the mystery of a falling cat. If you have a cat, but don't do this experiment. But if you hold the experiment, if you hold the cat upside down and you let it go under the effect of gravity, it lands beautifully in its 4 feet. In other words, it doesn't move with the same shape. And this was a very interesting problem that people wanted to take a snapshot of this process. And Marie was the first one to develop a technique that I don't have time to talk about, that you can take snapshot of the cat as it's falling down to prove this idea. And in fact, see, now we know that it can land. It lands beautifully on its feet. So how can you do this? The cat, you see it with your eye. Mr. Marie saw the cat with his eye, but he timed it right. So he had the time, and the shape he can see with the eye. In our case, if we study materials, we can't see it with our eye, because the scale of distance is nanometer. It's a billionth of a meter. And the scale of time scale is the femtosecond. So we wanted both the space and the time. And so for this, we had to break boundaries by making electrons out of light. So we used light to create electrons, and this is a tabletop at Caltech that we can do. We don't do the other techniques which going into the very short wavelengths and building big facilities like the synchrotron. And so the electron microscope is well known, and in fact it's 1930 was developed, and it was awarded the Nobel Prize here. Mr. Ruska, who did the first electron microscope, which allow you to see now an object that is extremely small, nanometer or so. So, but it didn't allow you to see motion of this object, and that was our development over the last 10 years, by which now we can make the electron microscope not only to see the object in space, but also to be able to see the dynamics of the motion itself. And this is an example of how it works. So the light pulse propagates, and then we split this by a variety of ways, and it goes into what we call a photocathode to create an electron pulse, and then they meet again at the specimen, and as a result of this, we can see an image of a nanometer scale, but now we can take snapshots as a function of time for this object. So we have now about 10 orders of magnitude increase in the time resolution and the atomic, maintaining the atomic spatial resolution of the material. We published quite a bit since 2001, not quite a bit, but in a variety of directions and applications. And I just want to share with you, for example, a few things. So you can do nowadays nano structures, like a nano arm that you can move. And this is actually in a real dynamical laboratory experiment where this nanostructure now have an arm extending, and it's moving in 3 dimensions. Please note that this is 1 over billionth of a meter here. We played also with other things, like, for example, musical system. This is a nano piano, and this is a nano harp. It's very nice music, see, but it's on the nano scale. You can't see it with your eye. You can do, this is the piano instead of the harp. And we did something that's interesting. We can control the melody itself by giving a sequence of certain pulses, and then we can have only one of the keys to play. So we have fun. We can do music, and that's what the National Science Foundation is supporting us for here. can also go into the biological world, and we have done that. This is a cell. This is a bacterial cell in front of you, but this is a whole cell, unstained, and now we're seeing the cell boundaries using a technique called PENM, which we published recently in Nature. And you can light it up. You can see all the membrane of that cell as a function of time in terms of the field that we have generated as a result of the interaction between the electron and the light itself. This is a very recent experiment. We all probably, if we live to 100, we will get Alzheimer. And there is a claim, and it's by very distinguished scientists in Cambridge, that the reason for the Alzheimer that you form amyloids. Amyloids are almost a chain of this protein, and there is a very important question: how stiff are these amyloids? If they are very stiff, they can influence our cells and prevent the communication, if you like, between the neurons, and as a result, we lose our memory. So we did experiments with these four-dimension techniques to actually get how stiff these amyloids, and in fact, it's remarkably stiff, and they aggregate to a large extent, and a lot of research now is going about can you generate some drugs, actually, that prevent this from happening. If you are interested, there is a very recent book we published about a month ago about our effort in this four-dimension visualization. Now, we couldn't have done this without all these people, and you would not recognize this, but I just wanted you to know that I haven't done this work. There are so many people that are involved in such research activity. So, then I want to ask you the question, two questions I'm going to ask in the end of my talk. And that is, light and the future of civilization. That's one question I want to ask. And we have challenges here. We have challenges in medicine and biology, understanding, diagnosis, and curing. We have a challenge in alternative clean energy, you will hear about. We have challenges in global warming. We have a challenge in water. Water is going to be a very serious problem. We don't talk about this usually. We only talk about energy. But water is a very serious problem, and so is food and population. And the exciting new development in nanomachines. Nowadays, people are designing nanomachines that you will see that have unique function into our cells. And finally, the thing that I think is very exciting is also space exploration and information technology and communication. So I'll just give you a quick review. First, there is a field now called physical biology, which combines physics ideas into biology, trying to understand, if you understand atoms and molecules, can you predict what a cell will do or an organ will do? We are far from that. Nobody in biology will claim that nowadays there is a lot of work and it's very exciting, but we are not there yet. Medical development. I give an example, for example, from the work of Katrina and Suna Lund, and tremendous amount of work has been done about using lasers in medicine and in a variety of areas. Alternative energy. Here is a reference I give, and I guess he will talk more about this. But a lot of effort now about the solar energy, especially in countries, for example, like in Egypt. I mean, the sun is almost the whole day is there, and we should exploit this. There's also the talk about artificial leaf, in other words, mimicking photosynthesis. Can we mimic photosynthesis? Until now, we haven't been successful, but lots of research is going on in this alternative area. Global warming. Sadly, lots of politicians don't believe in it yet. And it's remarkable that about 3 days ago in the New York Times, it pointed out that the year 2014 is the hottest year in the history of mankind. And yet, still, some people don't believe in such thing. There is the nano-micro-scale machines. And this, to assemble from first principles, that's the idea of getting the atoms. Like, for example, this machine here you're seeing of ribosome, which is synthesize in our cells the proteins that we need. Can we make this from first principles? Can we make a cell, even a bacterial cell, from first principle? These are very exciting and challenging problems. 1980, I wrote a piece in Physics Today saying it may be one day that we can control a chemical bond. Believe it or not, this nowadays is crucial in something called monoclonal antibodies, meaning that if you can get an antibody to be selectively going, say, into a cancer cell at a particular antigen, you made a breakthrough for hundreds of thousands of people, if not millions of people. That selectivity and control is not there yet fully. Information technology and communication, of course, it's now between cities and cell phones and everything. But I had the honor with my wife, Dima, who's in the audience, to be part of this going to space exploration at the Jet Propulsion Laboratory in Pasadena. And we saw the Mars Spirit. And the communication between the Mars Spirit on Mars and we sitting on the ground was 15 minutes. In other words, you send a picture from Mars and we receive it after 15 minutes. This opens up a whole new way of communication, and I also was present at the latest Curiosity landing. And I just want to share with you a small movie that really shows that this is an incredible achievement in the 21st century. And I hope we will continue to funding such ideas. This is a whole Mars science laboratory that was landed on Mars. Coming with this is a one-ton laboratory that's entering Mars and coming from a huge speed into zero speed to land on a particular site. This makes all of us proud in science and the engineering, I should say, and it's certainly something that I consider a breakthrough. It's just an art to think that you can land at a specific site on Mars. And that's prompted me to write an opinion piece to the Los Angeles Times about how curiosity-type research can create big stuff, like that Curiosity laboratory that you have seen, and that we should not be thinking about managing the research as we usually trying to do. I want to show you my own curiosity in the bedroom. I was trying to have a test tube, have a piece of wood, and I was burning with an oil lamp that in Arabic culture we make coffee this way, by an oil lamp. And then I was burning this, And I wanted to see, as a young boy, some gases that condense here on this water. And so when I did that, my mother was very happy because she saw me experimenting with some nice experiment, until she saw the flame coming in, and because I was actually burning this gas, and she really was very unhappy, actually. So this is curiosity. This is to play with things and to find out really what's exciting. This is the other question I'm going to raise about light in politics. And here I'm using light to enlightenment of our minds nowadays, which I'm concerned about. I have been very much concerned about science for the have-nots for decades now, and recently also science for the haves, because I'm seeing the haves are very comfortable and they don't want to support science as it used to be. So I believe a better world perhaps is what I call my 3 A's. First, we have to alleviate the not knowing. This is a huge population in the world of today, out of the 7 billion. So my belief is that education and science, especially education. And so we spend a lot of money giving F-16 and planes and tanks and all of that stuff. If you take 2, 3 F-16s, you can make huge effect on education of the world. Second, alleviating the not having. There are so many who are living on less than $1 a day in our world. And we give aids, and people give aids, but it's political aids. And I hope that we can have the aid with partnership to help these people achieve a better status. Third is alleviating the not free and helping liberty and justice by being consistent, by not saying one thing and using another for politics in order to do that. And I believe that all can be done. People say it's complex and it's very difficult. I know it's complex and very difficult. Everything is complex and difficult in life. But if we are serious about it, we can make a real impact. We need dialogues, not conflict. And we need vision and leadership. Leadership and vision, which we are not seeing nowadays in our world. Not hegemony. That's the key. We need really people of vision and leadership to understand the impact of this on our world. And that's why I have put some effort in my mother country, Egypt, over the last almost 15 years to build some science and education base. And the government called it Zowel City. We have now a city for science and technology. And it's a national project, and it's made of university, research institutes, technology pyramid to allow us to transfer the science into products. We have also Center for Strategic Studies in order to connect with the rest of the world, and a high school academy for those who are gifted. So I'm going to end by saying that space-time of our world is truly progress and peace in the year of light and beyond, and let's all enjoy life. Thank you so much. Thank you.